Oh, you're antisocial.
Okay, we'll start out in about 10, 15 seconds.
That was pretty good. Pretty good. More of those. Here come. Stay on the gas, and you'll be able to enjoy it. So not too much longer, but lots to do in the next month. I put out a couple homeworks for us. So I should say, welcome back, everybody. I put out a couple homeworks for us. I got the dates wrong on it. I said one of them was due on the 18th, and then one of them was due the next week on the 25th. I meant to say the 19th and the 26th. I looked at last year's calendar when I put down the dates. Those will be Mondays. So again, we'll just follow the basic rule. If I make it due on a holiday or a Sunday, it's really due on the next month. So that gives us 3 weeks for the EM homework that I'll be explaining a little bit today. Next time I'll come in, I'll run some code for you. I'll probably do it relatively quickly. The good news is I have a few lectures from last year that Sierra Marquez ended up presenting, and she walks you through this code. So she walks you through an R version, I'll show you a MATLAB version, and you're going to turn that into a big simulation study. See how well this algorithm works in different cases. What I mean to demonstrate, or have you demonstrate to yourself, in some cases it works really good, and in some cases it doesn't work very good. Okay. I've also given you a number of Chapter 7 homework problems, so work through those. We'll give you practice. We do have a midterm coming up next week. I'm going to rob back a day and not do that in class, and I'm going to give you another couple-day take-home midterm. So no huge pressure, but try to work through a bunch of problems. We'll still anticipate that we'll do an in-class final. We'll just see how that works. There's a number of students that can't make it for a number of reasons. So I think we'll just make it easy on everybody. That doesn't mean don't study lots of problems this class. There's no secrets. Read book, work lots of problems. So if you're not understanding why something might work, figure out how to implement it. So if you can think of it as a process, you understand why it works, then it'll make the math make more sense. At least that's a process I oftentimes go through. Okay, back to the EM algorithm. 2 steps. And I want to be a little bit clear that oftentimes you're just doing this step. So we had a question at the end of last class. If we're able to work this function out right here, and we're able to write this down analytically, all we're doing is repeating the second step. So the first step says do some math. Okay, so there's a math problem up here. If I can write this down analytically, then we're just repeating this step over and over and over again. So it's really like a maximization algorithm, but we computed an expectation up front. And so what I mean is that whatever this function is, we'll write it down in the context of an example so that you can see this. The book does a number of different examples in this. You're just taking this value, you're plugging it in, and then spitting out a new value. Taking that and plugging it in, spitting out a new value. So all you're doing in the code is just iterating this step over and over again. For this example, we can write down this function analytically. And so you're just cycling through this step. Saying that, sometimes you cannot work this out analytically. And so you might be doing some sort of a Monte Carlo approximation up here. And you would be recomputing that Monte Carlo approximation. And so I'd be taking this value, plugging it in on the next step, and then do a Monte Carlo evaluation of everything, and then maximize. That's called the Monte Carlo EM algorithm. Okay, so Monte Carlo evaluation. So what does that mean? You sample a whole bunch of times from this distribution, and then you take the empirical average of all of this stuff. That's what Monte Carlo does. So Monte Carlo is just a fancy word for approximation that converges in a finite amount of time. The more time you're willing to run it, the closer your approximation is. The nice thing about this algorithm is this expectation doesn't need to be exact. You just need an approximation, so in the right direction. And this maximization step doesn't need to be exact either. So in this class, I'm not going to tell you how to take maximums, but I will tell you one theorem. That if I keep making progress, eventually I'll reach the top of the hill. Okay? So that's something I employ in my everyday life. I'm tired, I want to get to the top of the hill. What do? One step in front of the other. And eventually I'll get to the top of the hill. Okay, that's a pretty weak maximization algorithm. It won't guarantee you a global max, but it'll get you to the top of some hill. Okay, so if you do that for all hills, and then you compare the heights of all those hills that you've climbed, you'll eventually get the maximum. Okay, so we've all studied maximization algorithms before, maybe Newton's algorithm or some quasi-Newton or something like that. All the conditions on those algorithms would apply to this sort of stuff. And so what's the best maximization algorithm depends on the problem. The nice thing is in our proof, when we study that this thing converges, what our goal is in all of this is to find the solution theta hat, I'll say max, is equal to the integral of whatever my sampling function is. I'll say theta psi given data. And I'm going to integrate over the missing stuff, okay, over its whole entire space. So we're going to average, we're marginalizing, and then we're taking a maximum. You might be thinking that this is a likelihood function, or maybe it's a Bayesian posterior, or something that you want to maximize. So this algorithm isn't specific to statistics. It's a general purpose algorithm. But the way I think of it is what we're doing is we're averaging out the missing stuff. So we're being quite sensitive about the missing stuff and make sure that we deal with all uncertainties, and then we're maximizing from there. There's other solutions to this sort of problem, but this is one such solution. It's the EM solution. So it's a partial expectation and then a maximization. Maybe that's a good idea. We talked about that for a minute last time. So our goal is to maximize whatever this function is. I'm going to give this function a name right here. So I'm going to say this whole thing right here is f theta given our data. I probably should write that this is conditioned on data right here. But just keep in mind, throughout all of our steps, everything we do, we're going to condition on data. Okay, so just keep that in mind. We'll see that and we'll allude to it in this example. So I'm thinking, at least for the time being, that these density functions are Gaussian. But this could be anything in general. We'll make our lives a little bit easy and give ourselves names for this. So this is going to be sigma k, e to the minus 1/2 xi minus mu k squared over sigma k squared. And so theta in our case are going to be the pi's, the mu's, and the sigmas. And we're going to have a whole bunch of those. There's going to be cap k of those. So what I'm thinking of, maybe for k is equal to 3, is that this is a mixture model. So I might have 3 different normal distributions. They're centered at different places. So this might be mu1, this is mu2, this is mu3. There's some sigmas in here, sigma 2, sigma 3, sigma 1. And then these heights right here are going to be relative to the pi k. So the area under the curve is going to be pi k. Okay, so I'll just draw that in. This area right here. In our case, it's going to be pi 1. The area under that curve is going to be pi 2. I want to point out real quickly that if I told you what the mu's were, and I told you what the sigmas were, so if I drew this picture for you, and then I drew you little data points, what they look like right here. So for instance, let's say I imagine I have this data point. I'll call it xi. I can tell you pretty quickly, with some degree of belief, and I might even quantify this for you, and I'll tell you how we quantify it as we run through the algorithm, where this point came from. It probably came from mode 2, the second distribution right there. How do I know? Because it's close to mu2 relative to its sigmas. So if I told you there was a point over here, say this is another one, I'll call it xj. In that case, you'd feel pretty good about saying, I bet that came from mode 3. Probably didn't come from mode 1 because the tail for mode 1 is going to be really, really small. This is like 5 or 6 standard deviations out from mode 1, so probably didn't come from that. Where this algorithm is useful is when there's a high degree of overlap between the modes. So if this overlap right here was big, then the algorithm would be helpful. If we are living in a high dimensional space and you couldn't visualize everything, the algorithm is even more helpful in that case. The algorithm is going to work very well if these modes are well separated. If they're close to each other and overlapping, the algorithm will not work particularly well. And as we scale up dimensionality of everything that we're studying, the algorithm will become a little bit, I'll say, the algorithm has a harder time distinguishing the modes. So that kind of makes sense, that there's a lot of vacuous space in high dimensions. So the problem gets harder as the modes get closer. Of course, the number of modes is going to be a confounder in there as well. And then the dimensionality of the problem will make the problem harder and harder, longer.
So when you say the area is equal to pi 1 for that curve,
yes.
You're talking about the area of the curve excluding the intersection?
Yeah, that's right. So just under this one of the curves. Okay. That's right. So you can just do a little bit of mental math. What's the integral of this over x? So integral, sum k goes from 1 to cap k, pi k's, fx given theta k's, dx. What is that then? Probably should tell you one other thing in this, that the sum of the pi k's, k goes from 1 to cap k, is equal to 1. In all of these functions, they're probabilities. It's the probability of being in each one of the modes. So these are elements between 0 and 1. So what's this integral? I integrate over all of x space. This whole thing is x. Not 1. It's 1. It's a distribution. So the integral over these things, they're all 1 because they're density functions. But then I have these weights on top of everything. So these are going to be scaled areas, and these areas under the curve are going to be scaled to be relative to the pi k. Does that answer the question, Humphrey?
Yeah, I think so.
Super important problem. Knowing how to solve this problem makes you more of a modern statistician. Mixtures of things. If you don't know what distribution something is, maybe mixtures can be a good representation. There's a big overarching question, what's cap k? And we're not going to address that in this question, in this class. But if you're a Bayesian, maybe you can apply it on k. And that's what Bayesians would do. If you were somebody else, maybe you maximize over k. Be careful about overfitting everything. So very easy to overfit, so you probably need a regularizer in there. Bayesians have automatic regularization built into their problems. They have an automatic penalty coming in. The state of the art, I would say, for doing this is not to use a parametric prior. K is going to be an integer, so maybe you're inclined to think, maybe I use a Poisson prior. But of course, I have to parameterize that, and I need to state what the variance and the expectation of that Poisson are. So maybe you don't want to be constrained to such large assumptions. And so there's semi-parametric ways of dealing with this. Dirichlet processes are what that's all about. We're not going to cover it in this class. But in your future, I'm sure you'll see it. So if you wanted to know what that key thing is, Dirichlet processes, it's about this problem right here in co-estimating k. If you didn't know what k was, what you can do is you can run this algorithm for some k. Maybe you take k is equal to 2. You run it, see how well everything fits. You use a fitness criterion. Maybe you look at log likelihoods and you penalize it. Maybe you know what BIC is, AIC, something like that. Some model selection technique. And you look at the AIC, BIC, or whatever your model selection technique is for k is equal to 2. And then you do the same thing for k is equal to 3, do the same thing for k is equal to 4, and you compare all those to each other. And you see which one you like best. So that's not the way I would do the problem on co-estimate k, but that's at least a way that you could approach the problem. For your homework, you're going to get to assume you know what k is. So it shouldn't impede you on the homework. Just keep in mind, there's fancier incarnations to all of this than what I'm telling you right now. Okay, so in our problem, to sample from this mixture model, and I'll run some code for you next time. I don't think we'll have time this time. We'll sample from this, we'll run the EM algorithm, and then I'll give you an online version of the R code that Sierra coded up for you. And she'll talk you through that. I'll post a link to the Slack page. So that'll all happen on Wednesday. Okay, if I got to see everything, we talked about this, if I got to see the CIs and the XIs, this problem's easy. So I wouldn't even have to guess which mode things came from if I got to see the CIs. In this problem, I'm going to say you don't get to observe this. So this is going to be missing. So that's the part that's missing, and that's what we're calling psi in this problem. So psi, to us, are all of these labels. C, N. What we get to observe are the x's. This is our data. The x's. And I want to learn the thetas, and I also want to learn what the pi's are as well. So that's the name of our game. We're not going to prove right away. We're going to just walk through this example, and then we'll come back around and prove that this algorithm actually solves the right thing for us. We're just going to employ the algorithm. We're going to work out this function right here. On the homework, I'll have you work out these maximizations. But to make sure you're on the right track, I'm going to tell you what the maximizations are so that you have the right thing to code at. That's on the homework sheet already. So there's an EM handout for you, and it does have your maximizations written down. I'll say what they are after we get through this. Any questions before we try to write down what we need to do to implement this algorithm? Let's work on Q. First thing we need to do, we're going to do all of this, we need to write down the likelihood function. So in the context of our problem, this will be the likelihood. Of course, I'm integrating over something. So I'm turning something into a random variable. I think there's only 1 gig in pounds for doing that. You can think about it how you want to. There's other words than saying posterior. I'll tell you what they are after we write down what the posterior is. Okay, so our likelihood function. Given data, in the context of our problem, that's going to be the likelihood of mu's, sigmas, pi's, I'll say k's. K goes from 1 to cap k. Then I have all of my c's right here. So this is going to be C1 to Cn. These are my labels. I don't get to know those. I'm going to integrate these out. And then we'll do the maximization. And this is going to be given my data. This is going to be my x's. So that's what we're working on. I said to everybody, try to figure out what this likelihood is. I'm just going to write it down for you. I can just stare at this thing. This is all I ever do, is stare at this function. And then I try to write it down correctly. I just want to point out, the way that I wrote this down is, I've got CI over here that I'm sampling, and that's going to be my index for everything. I'm going to change this notation just a little bit. It's exactly the same thing. I'm going to say K right here, and then my CI is equal to K. Easy stuff. So whatever this is, whatever K value that is, I'm going to plug it in right there, and I'm going to just index it here. So this looks a little bit superfluous. I kind of like it because it makes it seem like C is a random variable. So I can look and feel, what do I want to do? If I am going to upgrade something to a random variable, I'm going to multiply by its prior. I'm going to take my likelihood function and multiply by its prior. And it's going to feel very natural if we use that notation. So our likelihood function, everything's IID. That's a big hint. I've got a big product right in here, n things. And then I'm just going to write down sum K goes from 1 to cap K. Fx, I'll put in my pi k's in here. Fx given my mu k and my sigma k. And I might want to write down that Ci is equal to K in all of this. And I'll put down an Xi right there. What do you think of this? So I've asked you all to think about what the likelihood function is. Is that it? Kind of looks and feels right. Just took a product over the thing that I wrote down. What do you think?
Don't we need a domain for the x's?
Slightly louder.
Sorry, don't we need the indicators for the x's?
Gotta have that indicator in here. So if I wrote this thing down right here, you would notice that Xi is appearing in K evaluations. So there's a big sum right in here, and I'm plugging the Xi into every single one of them. There's a big problem, because Xi didn't come from all three of these modes, it came from exactly one of them. So we don't want to place it in all of them. So I just want to write down the delta function that Xi comes from component K. That's important enough to write down really big. So we could give that some notation. So this might be, I'll just write this down, maybe Xi is going to come from Ci is equal to K. So same thing, just going to make up some notation for it. Okay, so when I go to run the EM algorithm, I need to take an expectation over this thing. What am I taking my expectation over? I'm going to be taking it over what's missing. That's going to be the C's. And the only place my expectation operator operates is on the delta function. So if that wasn't there, we wouldn't know what to do. Okay, so let's just write this down a little bit different. I'm going to make it simple for us, and I'm just going to take K is equal to 2. Just so we can make the notation a little bit easier to work with. And everything will generalize. Let's work out Q for K is equal to 2. everything will generalize. This is what I always do. I see a K in there, I usually do it for like 2 or 3, and then I go back and I complete my proof, and I look at my steps where everything was easier to write. However you want to do it is fine with me. So our likelihood function is going to look like this. It's going to just look like pi 1 f x I given mu1. Well, let's just write it down with the Gaussian stuff already in there. So 1 over 2 pi sigma 1 e to the minus 1/2 xi minus mu1 squared over sigma 1 squared plus pi 2. 1 over 2 pi sigma 2 e to the minus 1/2 xi minus mu 2. I need to do my indicator functions. I have a big problem with this. So xi is going to come from c pi is equal to k. This is going to be c pi is equal to 1. Delta function xi element ci is equal to 2. It's going to be my notation for that. Let's see if this bothers anybody. Can I get rid of those? Remember what I'm going to do. I'm going to take an expectation over everything. Everything will just slide out the front. Then I'm going to maximize. And so if I do some derivative-based maximization, all of that stuff is going to cancel. So I'm just going to get rid of it up front. So you're maximizing something. It doesn't matter how you see it. It's just raising that function up and down. So I'm going to get rid of that. And I'm going to rewrite this just a little bit differently. And I've got my big product right in here. So I can certainly just take my sums and just drag them over everything. So I guess maybe I'll just leave this out.
For the second part, why did you write?
Why did I stop writing? Squared sigma 2 squared.
Okay.
My brain had just told me I was done. So I need to take a logarithm of all of this stuff. So we already know what much of this is going to do. This product is going to come up here, and it's going to be in the sum right here. And so I can just do that. And just bring that sum over. This is, of course, going to be, all these are going to get end up right there to the end, and I've got my sum. Okay. So I'm just going to rewrite this just so we can see what's going on. This is going to be sum. K goes from 1, cap K. This is going to be sigma 1 n over that e to the minus 1/2 sum I goes from 1 to n xi minus mu squared mu1 squared sigma 1 squared. Whoops. 9 a.m. stuff. I've got this indicator function sitting right out in front. I'm just going to leave that as a placeholder, just real quickly. I'm going to rewrite it in just a second. So this is going to be plus, oops, I've already got my plus in there. So this is going to be k And then I've got my pi k's right out in here. Okay. So no big deal. There's pi k's right out in front there. Guess that doesn't look too good. That looks horrible, doesn't it? Just let this be. Sometimes it's best to just start over.
Oh, sorry, what?
Yes.
For the delta functions, should they be products? Like product from I equals 1 to n delta xi.
Where do you want them? So right now I have everything written down additively. I'm going to rewrite it in a second. That's kind of where I'm going with it.
Okay.
So let's just see if I can write something down real quickly. So this is going to look like e to the minus see if we can just do this again real quickly. There is a big product over here. I've got my sum. K goes from 1 to cap k. Bear with me. I'll eventually get this written down well. Xi minus mu k squared over sigma k squared, and then I have this delta function right here. That's what we wrote down before. Shouldn't be any major point of contention right here. So I wrote this down in an additive way. I'm going to take a logarithm of all of this. But before I do that, I'm going to rewrite this just a little bit differently. So I have this expressed as a sum. I'm going to rewrite it as a product, and this will make my life very easy in a second. So let's just see if I can do this. Logarithm. This is going to be my product. I goes from 1 to n. And I'm going to re-express this in just a second here. There is a 1 over sigma k right in front of there as well that I forgot to write down. Let me just ask the question. It's kind of obvious. In this sum, for each I, how many terms appear right here? Let's just go back to general k for a second. So Warren said 2, he's thinking cap k, Steven said k. Does anybody else have a different answer? It does look like there's k terms. What if I said there's 1? Yeah, so it kind of depends. All of them except for one of them is 0. So when I add things in, I could say, hey, I've got some number, it's 5, plus 0, plus 0, plus 0, plus 0, plus 0, and I could do that all day long. And if I kept telling you I was going to do that, you'd tell me to knock it off and just say, the number is 5, stop adding 0 to it. Okay, so there's one term in here. Of course, there are k, it's just that k minus 1 of them are 0. So I'll say there's only one. Non-zero term. I'm going to rewrite this down using a product. And there's only going to be one term in this, the way that I write this down. So when I add things together and I keep adding 0, I don't do anything to it. It's kind of like multiplication. When I just keep multiplying by 1 over and over again, I don't do anything to it. So I'm going to re-express this that way. So this is going to look like e to the minus 1/2 sum k goes from 1 to cap k. And I'm going to rewrite a whole bunch of this stuff in here. I'm going to take a logarithm of these things, and I'm going to throw them upstairs. So I'm going to write down that I've got an xi minus mu k squared over sigma k squared plus a logarithm of pi k minus a logarithm of sigma k. Give myself just a touch more room. And I'm going to put my delta function right here. That xi is going to come from component k. So think about what I did. I just ended up putting a whole bunch of zeros up in this thing, and there's only one term that appears. It's exactly the same thing when I write it down. So I only have one of these functions that's going to appear right up here. So there's only one term there. I'll let you go through the algebra and convince yourself that those are exactly the same things, but I threw this up in this big, I ended up writing this down like this. K goes from 1 to cap k. Maybe like that. So this part, it just subbed in for that. So instead of expressing this as a big sum, I have it as a product. Right here. Maybe that's the easiest way to write it down. So how many of these things, so this is a 0 or something not 0 up here, and I'm just plotting it all together. This is identical to this. This is the nice step because it makes everything really easy. Let me show you. Let me take out those products right there. Both of them are products, and I'm going to write them down as sums. I goes from 1 to n, k goes from 1 to cap k. Same thing, just expand it. So I guess I was going to do this for k is equal to 2, and I just decided to stop. So I went back to just regular k. If that confuses you, just work out the left and the right-hand sides, and you'll see that they're exactly the same. So I'm using the indicator kind of in two different ways. At first, I used it in an additive way to express everything, and then I turned everything into a big product because it makes my likelihood easy to express as a big product. And so I moved the indicator function to the exponent. Okay. That's the hardest part of this. It's just figuring out the way to write down the likelihood so that you can work everything out algebraically. Exactly the same functions. Okay, now everything's kind of easy to do because I know I take this logarithm right here. As easy as can be. So this is just a lesson in how to write things down the right way. If you write things down the right way, everything works out great. So now my log likelihood function is just this stuff that just appeared in the exponent. This is I goes from 1 to n, k goes from 1 to cap k. And then I've got all this stuff in there. So this is xi minus mu k squared over sigma k squared plus logarithm of pi k minus the logarithm of sigma k. Cool. Oh, and now I need the most important part. My delta function, xi, comes from component k. Any questions about that? A little bit fast for 9 a.m. maybe. Maybe that's just me because I'm standing at the board. Okay, now we're ready to do EM step 1. We're going to take the expectation. So Q theta. I'll just write it down notationally. You know what my thetas are. This is going to be equal to the expectation of this thing. This is going to be equal to minus 1/2, double sum. I goes from 1 to n, k goes from 1 to cap k. Xi minus mu k squared over sigma k squared plus logarithm pi k minus the logarithm of sigma k. Then I've got my expectation over here on my indicator function. Indicator function that xi came from component k is what that says. So somebody help me out and explain this to me. I'm going to say that this is the probability. Xi comes from component k. Wants to tell us why. Expectations of indicators or probabilities of that indicator. Why?
Because the indicator can only take on a value of 1 or 0.
Yeah, that's true.
And so if the indicator is equal to 1, that means that you're weighting it by the probability that it's occurred, and then the 0 part cancels out. So
that works for me. Anybody else want to say something similar? You'll say the exact same thing, but
Expectations are averages.
yeah. So I guess all that works. Maybe it's just too simple. So if you think about xi's or Bernoulli's with probability p, right here, expectation of the xi's, this thing could be either a 1 or a 0. That's what it's going to be. So this is going to be 1 times p plus 0 times 1 minus p. That's how we do the expectation. That's p. So if we just think about Bernoulli, the expectation of a Bernoulli is its probability. So expectations of indicators are probabilities of that event. So this is a probability statement. And what I need to figure out is what is the probability that xi came from component k. That's where we're at. Probability of this thing. Now I'm in business. That's a word I like. They're all about probability. So the probability that xi is an element of component k. I'll write it down like that. Same thing I've been writing down. Just kind of impressing upon you. I can make up notation on the fly. So lots of things that we could write down. I could call that CK maybe. Made up a new thing, but this is what we are calling CI is equal to K. How do we figure that out? So let me just help you out. We know what f of xi looks like given mu k sigma k and Ci is equal to k. So what I want is maybe something that looks like this. Probability that Ci is equal to k given xi and everything else. mu k, I'll just write down everything. Mu k's, sigma k's, pi k's. K goes from 1 to cap k. So given knowledge of all of the model parameters, I can maybe compute that for you. I know this thing. I know the conditional flip of it. I know what xi's look like given all of that stuff. And now I want to exchange the roles of xi and ci. So given ci, I know how to generate the x. Given xi and all the other parameters, I can tell you what the c is. How do I do that? Bayes' theorem. Yeah, that's it. So that's the whole thing that people are like, don't say EM is Bayes. But it is. So there's always this Bayesian step. So this is going to look like this. F xi given the mu's, I'll say mu k, sigma k, ci is equal to k. And now I need my probability that ci is equal to k. And I need to normalize this. This is Bayes' theorem. So I'll marginalize over k. F xi given mu k, sigma k, ci is equal to k. Probability ci is equal to k. So I think of this as Bayes' theorem. I think of this as the posterior probability of the c's given the x's. Some people don't call it that. So I'll say this is a posterior. And if you find somebody particularly fussy about doing Bayes, I'm not sure that happens anymore, but there was a time where people would freak. You had to like pick one thing or the other. Can possibly be a Bayesian if you're a frequentist. Hopefully I've explained to you Bayesians can be good frequentists and frequentists can use Bayesian methods. And you can conjoin things. I've heard this called the reliability index. Here machine learners call it this. Look at the reliability index. You mean the Bayesian posterior probability? I've been there too many times. Whatever you want to call it, you can call it. So what would I pick this to be? I'm just going to give it a name. I'm going to say pi I k. Pi I k. We'll exploit that later on. There's a couple different ways you can go about this. If you're doing a full-blown Bayesian thing, you probably wouldn't index that over time. But if you're just an optimizer, then you might index that over time and put that into my maximization function. I'll say a little bit more about that, but there are two ways to deal with this. Sometimes people will not even write that thing down right there, and they'll just let this be 1 over k and it cancels out. I didn't use it prior because everything's canceled out in my equation. Maybe Fisher would have said something like that. I'll just write down what this looks like right here. This is going to be 1 over 2 pi. Sigma k e to the minus 1/2 xi minus mu k squared over sigma k squared pi I k over this big sum. This is k goes from 1 to cap k, 1 over 2 pi's. Starting to notice that 2 pi thing never seems to matter. E to the minus 1/2 xi's minus mu k's squared over sigma k squared pi I k. That's what that posterior probability looks like. These things are canceling. This whole function right here is the bulk of everything that's driving everything. Your posteriors are proportional to that. There's one part that we didn't address in all of this. When we took this expectation, we wanted to take the expectation over the CIs, given all of my old parameter values. We didn't write that down. So which parameter values am I integrating with respect to? I'm supposed to know those. I've got to plug something into this equation. We don't know them yet. So what I really need to write down is that these are indexed by t. Now, full-blown Bayesian wouldn't let that change. You would think that that's some sort of a violation of some principle. But in the optimization context, it makes it faster to end up converging to this maximum if you let it change. So which parameters am I plugging into all of this? Theta t, or theta t's in there, which are my mu's, my sigmas, and my pi's. And that's it. So here's what we're going to do is we're going to maximize this function. And I'm going to write this down. I'll come back next time, maybe work out one or two of these for you. But I'm going to leave the rest for homework. That my pi hat t plus 1, my mu's hat t plus 1, and my sigma hats t plus 1. So I'm going to get these by maximizing this function. I think we're over. So I'm going to just leave that till next time. We'll pick up right here, maximize this. I want you to remember that there's a constraint on these pi's. That the sum of the pi i's, k's, k goes from 1 to cap k, this is equal to 1. So there is this constraint in here. And so if you're going to solve for your pi's, you need to adhere to that constraint. Does anybody know how to do that? What did they teach you in calculus? Constrained optimization.
Lagrange multiplier?
Lagrange multipliers. Yeah, so you maybe set up the Lagrange multiplier sort of thing. I'll come back, I'll do that one next time. Let you do the mu's and the sigmas for homework, but I'll do the Lagrange multiplier to remind you. Then I'm going to run just a little bit of code, show you what goes on with this. I'll explain EM homework, and then we'll be moving on. I think the next thing up is the Kramer-Rao lower bound. So if you want to have a quick preview. That's it for now, you guys. We'll see you on Wednesday.